Hi, good morning, everyone. First of all, thanks very much again, Alan, and the guys from CitA for having us over. So my name is Jandré, and I'm in charge of the materials and 3D printing operations at Hardcore Technologies Limited. So what we are, we're essentially a construction technology company who utilizes 3D construction printing, which is the most commonly well-known term for it. But the more sort of industry favoring term for it these days is additive construction. So which is essentially construction by additive manufacturing, essentially. So that's what we're mainly focusing on. And during this, I'll essentially showcase a recent project that we completed in County Louth in Dundalk, which was for Louth County Council. It was a social housing scheme. So it was the first social housing scheme for 3D construction printing within Ireland. And as far as we know, the rest of the world as well. So I'll just briefly give you an overview then of how this technology works and what it is, and then show you a bit of a case study on our recently completed projects. So then, who are we then, and where do we fit in? So as most of you are aware, there are 7 categories of MMCs, modern methods of construction. And then we slot there into category 4, which is additive manufacturing of structural and non-structural components. So as most of you are aware as well, most of modern methods of construction happen in a factory setting where it's manufactured in a factory and then transported to the site where it's assembled. So we sort of in this unique environment where we can either do it in a factory setting and install on site, or we can directly, as we call it, take our factory to site. So what that essentially means is we can take our equipment, put it on the back of a truck, transport it to the site, set it up, and then essentially have our factory directly on the site. And then what this essentially achieves for us is during the process, we utilize the benefits of the technology, and one of the benefits is speed. So we essentially then take our digital model directly from our computer model, and it's being executed directly from our model on site. Because we're essentially, as I'll talk a little bit later on about a process as well, how the process works is it takes your drawing, your CAD, your digital model, it takes that and creates a set of coordinates. So it's X, Y, and Z coordinates that gives instructions for the printer to follow. So the printer can't deviate from its path. So the model you enter into the software is the exact path that it follows. So what that essentially means in practical terms is extreme precision and efficiency. So we're very accurate in where the material is placed. And what that essentially then allows us again to do is go for a just-in-time procurement procedure so that we can prefabricate and pre-order most of our components, so that once the design is frozen, we can send those designs to our manufacturers and we can tell them, you don't have to come to site, measure, and then fabricate. You can take these drawings as is and fabricate. And it's a 99.9% chance of success that it will fit. So then what that essentially does is lead to reduced construction timelines, and then ultimately leading to an increase in the housing output, which is what we're trying to focus on. So then what's this problem then that we're trying to solve? So within essentially ever increasing demand for housing within the market, we have an ever decreasing skilled labor force. We're basically comparing ourselves at the moment to block construction. There's very few blockies that graduate every year. So the skill force for block construction is ever decreasing. And then we essentially want to use innovative new technologies and automation to ramp up the supply of housing by using less labor and ensuring more quality at the end of the day. So then in terms of speed, we're about 25 to 30% more efficient in terms of construction. So on the superstructure itself, during the project that we did recently now, we saved 65% on the overall superstructure buildup. So we compared ourselves to a block crew of 2 crews building the same exact superstructure, and then took ourselves then as a comparison between traditional versus using 3D construction printing. And then from that, we achieved a 65% more time efficient process in return. Then if you look at it, entire construction timeline, so from breaking ground, superstructure, all the finishes, all the way to handing over the keys to the new owners, it was a 35% improvement in shortening the construction timeline. So that's one of the main benefits, is the speed of using this technology. Secondly, is you're reducing labor. We only need about 3 to 4 operators per site, so operating the machinery. And using the machinery, you're increasing as well your automation. So you still have 3 to 4 operators on site, but they're not as heavily involved in manual labor. So the machine is essentially there to do all of the hard work, all of the heavy lifting, and the personnel on site is essentially just there for monitoring and doing sort of very much less labor intensive tasks. So that's about a 40 to 50% decrease in saving on labor as well. What that also does is increases your or decreases your risk for health and safety on site. And then we're also trying to leverage new technology by promoting digitization, which again gives us the advantages of using the accuracy of the technology. And the material that we use is fully compliant EN 206 concrete. So we partner with Roadstone, which delivers our material for us via ready-mix trucks to site. And so what that allows us is to have already fabricated or already approved and certified material that arrive on site. So we essentially then just use their material to speed up the process. And because we're comparing it to block, essentially, we're about 5 times stronger based on the same exact design. The average strength of block used currently is about 14 MPa, whereas we come in around 50 MPa at 28-day strength. And the main reason for that really is the addition of additives into our material. So we need a specific rheology and flow of our material to achieve good properties for the process. So essentially what that means is the material needs to be flowable, to pass through our lines and into our printed. But as soon as it's extruded, the material needs to be hard enough and stiff enough to carry the weight of the subsequent layers without slumping or deforming. So that's essentially the science behind the material, is to get that process right. And that's the reason essentially that the material is so much stronger. And then in terms of tolerance, due to the accuracy of the machinery, we have about a 5 millimeter tolerance over 10 meter spans. So that again allows us to then prefabricate our joists, our roof trusses, etc. And using the concrete material that we're using, we are inherently fire resistant and provides great acoustics for the building. And then a hot topic, again, sustainability. So a good benefit of using this technology as well is the accuracy of placement of the material. So you can program into your model that the printer is executing on site. You can program in all your openings. So if you want to include openings for wall sockets, light switches, etc., you can program all of that in. And essentially then the machine won't place material where they are set to be. So it essentially just places material exactly where it's needed. So that minimizes your waste, which in turn leads to less material usage and less wastage on site, improving your sustainability. The machinery that we use as well uses an open source material platform. So essentially what that means is we can use any locally sourced material available on the regional location to where the site is. So it essentially mitigates having to use bagged material imported from Europe to specifically use for 3D printing purposes, which was previously done for projects using 3D printing worldwide. But we've now developed a material that you can use locally sourced material, which decreases your carbon by about 50%. And then the material that we've created alongside with Roadstone as well is the lowest carbon embodied material for printing purposes that currently exist. And then taking all of these factors into account, we then provide project certainty by delivering on time within the cost parameters, and then in turn delivering the value. So then if I give you a little short just process overview of how the process works, it starts off with your traditional design. So whether you design it in AutoCAD, Revit, it doesn't really matter from there. All that the printer is interested in is the center lines of your building. So essentially you then export your center lines into a step file. So that's as you go into your CAD height of your structure, you give it a layer height, it then slices that building up into printable layers. So then from that, once that's completed, you give it a layer width and a layer height, which is essentially the parameters of your wall. It then generates a G code. So that's essentially then your XYZ coordinates that the printer follows. That then gets put into your printer software. So the computer that essentially controls the printer, which it is then ready to execute on site. So we then, once that's all ready, so that happens before the printer is taken to site, the printer can be brought to site and assembled. So that's about a 2-day installation plus calibration. So we set up the frame on the first day, and the second day essentially for plugging in all the cables and ensuring that it runs on the right track and it's all in the right orientation. And when that's ready, we get the ready-mix concrete truck to site. It deposits the material into a concrete piston pump that then feeds the material through a series of hoses up into our printhead. And then at the printhead, it gets dosed with that accelerator to get it proper material properties that we require. And then from there, it builds up your structure layer by layer. And then in terms of our regulatory compliance, essentially, there's 2 ways of currently designing to existing norms for 3D printing. So it's either according to Eurocode 2, which is your standard reinforced concrete design, or according to Eurocode 6, which is your masonry design. We essentially, the most easiest way for us to get to market was to follow Eurocode 6 design, as that's the most common building method within Ireland. And as well, what that does, it allows us to place all of the structural load on our actual 3D printed walls without the use of any reinforcing. So that's the way we design currently. And then in terms of the material that we use, it's a fully compliant EN 206 material, as I mentioned, that we obtained from Roadstone. And there's been recently a new standard as well that's published. It's an ISO ASTM standard. So it's an international standard that has been adopted by the NSAI. And essentially, it's a standard for ensuring quality control and for additive manufacturing for construction. So it's for structural and non-structural components. And then we, during the project in Dundalk, that I'll talk about now, we were the first to be regulatory compliant and achieve conformance with this new standard. So we're very proud of that as well, in terms of ensuring proper workmanship and quality on site. So then what I'll show you now is, again, just the project we've completed for Louth County Council in Dundalk. So essentially, it's a terrace of 3 houses over 2 stories. So it's designed exactly according to a social housing specification. So it's 3 houses consisting of 3 beds each having a square footprint of about 110 square meters. So the overall structure size is 350 square meters. Print time for this was 12 days. So that's the time the printer was on site constructing the walls. Overall time for the printer being on site. So that includes us taking the printer to site, installing, taking down at the end of it, adding in your joist hangers and your joist in between the 2 floors, as well as the scaffolding rise throughout the structure build-up. It was a total of 18 days for the superstructure to be completed. And then it consists out of fully load-bearing structural concrete that's EN 206 compliant. We achieved the A2 rating for the NZ accreditation, and it's a fully BCAR compliant design. So then there's just gives you an idea of the speed related to using this technology compared to traditional methods. So if you look at the entire project on the left-hand side, It's about 203 days if this was being built in traditional block by 2 crews. And then we achieved the entire project. So essentially, as I mentioned, from breaking ground, excavating the foundation to handing over the keys at the end of the project, it was about 132 days overall. So that saves 35% over currently traditional methods. And then comparing the wall system, so block versus the printing, it's a 60% saving on your superstructure timeline. So then essentially we use a C3037 concrete for this. We've done air tightness tests, so essentially our walls in itself is completely airtight. So all that we need to essentially have an air tightness membrane around is your ceiling and your window and door openings. And then we've run tests as well on this, and we've achieved the 0.3 air changes per hour, which is better than passive level houses. So it's a very good option for robustness and using the density and the thermal mass of your actual structure for the benefit in the overall sustainability and life cycle over the entire structure. So I'll now just show you a bit of an overview video from the process. So this is the site there in Dundalk. So we started for excavating the foundation. So it was a traditional strip footing foundation. On that strip footing, we used precast rising walls along with a precast and insulated slab. Once that's installed, we have a crane bringing the printer to site, or it's arriving on a truck. We have a crane there to install the frame, which takes about a day. Second day for calibration. Once that's all set up, we're ready to receive material on site. And then once the material arrives on site, we load our code. So the path that the printer follows, and then that is used then to build up layer by layer. So it's a cavity wall design. So it consists essentially out of 2 leaves of 100 mil each with 150 mil cavity in between. So we tied with wall ties as well for stability. So it's a masonry design to the T. And on the inside of the cavity, we then pump it in with a mineral clay pumpable insulation, which is also a fire-rated insulation. So essentially that allows us to have our fire compartmentalization between units. Then for floors, we essentially use a traditional joist hanger and quasi-joist system. For lintels, it can be either prefabricated concrete or prefab steel lintels that's insulated. For this, we just use precast concrete lintels. So they're essentially, we leave the gaps for them during the printing process. We then essentially can just place them into the position, and then we can print straight over them again. So it's a very simple process. And then on the inside of the building, we use essentially a studding frame. So we have metal studs and plasterboard. So we run all of our services behind our plasterboards. So that essentially allows us to have no drilling or cutting holes or chasing of any wires within the building. And then on the external, we essentially apply a rendering on the outside. But there's different options available for that as well. But this is essentially then the time lapse of the process. And that's what it currently looks like. So we're having an event tomorrow where we're officially launching it and handing over the keys. So that's very exciting for us. So then if we look at this, there's the printer nozzle going on, extruding the material. So that's what the process looks like on site. You can see there the cavity wall construction with the wall ties in between. So that's essentially what's happening on site. And then during this project, we essentially built up in 7 sequential phases. So it's essentially, we go from the rising wall up to our DPC level. We then install our insulation as well as our slope DPC. And from there, we can go, essentially, we go from our DPC to our sill level, from our sill to our lintels. We then install our lintels, from lintels to floor plate level. Then it's a day or 2 that's down, that's not printing, where essentially where you're installing your joist hangers with your joists. And then from there, it's the same process going up to your eaves level as well. So then just lastly, to finish off our detail, So that's essentially what our detail consists of. So if you start from the ground up, we use traditional strip footing foundation. So in essence, what this essentially means is it's traditional construction apart from the buildup of your walls. So you're replacing just placing manually by hand and using automated process and more efficient process and using a 3D printer to place your walls much more accurate. So then traditional strip footing foundation, we've also realized it's much more efficient when you decouple your foundation system from your wall system. So we essentially use prefabricated and precast components for an entire subfloor system. And then that essentially allows us to only bring the printer to site once that is ready and ready for us to start with the superstructure. So you're saving about a week's time again, where you don't have to be on site printing the rising walls. So if you use precast systems, it's much more efficient. You save a further week on site. So we use prefabricated floor systems. Then we 3D print our walls. Once the walls are sealed, the roof is up. We then come in, drill a hole on the inner leaf, which is then used to pump in the insulation for the cavity.
You're pumping the insulation?
Yes, so the insulation is being pumped into the cavity. And then our inner system, we only print the external walls. So for the inside walls, we use either LGS partitions or timber partitions with a metal studding system. And then the roof system is a traditional prefabricated timber roof system. And apart from that, traditional. So thanks very much, everyone. And we'll welcome questions in afterwards. Thanks.